Okay, so the question is that this new problem that we've just discussed for high power lasers called thermal lensing here, thermal lensing, why is it called so? Because lensing implies that there is some kind of converging or diverging of a beam. So where does that show up here? So let's talk about that, and let me also just complete this figure here, that the Gaussian beam emerging from the laser, that's the intensity profile, and this is rho equals 0 in the middle. Okay, and so in this curve here also, that's where, this is the 0 point, and then rho is going on either side. Okay, it's increasing this way and that way. All right. So now why is it called thermal lensing? So the thing that happens is there is actually converging and diverging of the beam, because it's seeing regions of different refractive index here. So let's just see how that comes about. So let's say that you have let's see what happens, so let's just go with why call this thermal lensing. So let's just look at what happens when you have a medium. So here's the medium, and let's say that this is acting as a thermal lens, and all it needs to do to act as a thermal lens is that its refractive index needs to depend on temperature. So this is a thermal lens, which means N is a function of temperature. Okay, and let's assume first of all, let's look at this dependence of the refractive index with temperature. Now remember, if you look up here, the temperature is hottest in the middle because the beam is most intense there, and and then it falls off radially. So let's just assume that this thermal lens here has this profile. And it's also n of rho versus rho, and here's the 0 point, right? And the refractive index is falling off. Let's say it decreases with rho, so it's actually it's the black curve there, right? So let's just look at that. So let's say that the refractive index is doing something like this. Okay. So in this case, so it's the black curve there. So in this case, what's happening to the wave? So let's say that such a thermal lens whose refractive index is varying like that is impacted by a plane wave coming in. And it's a plane wave, so all the crests are lined up. So the crest, if you draw a line through all the crests on the wave, it's like a plane wavefront. That's why it's called a plane wave. So this plane wave, so I'll just say here, planar. So let's just say that this planar wavefront is incident on this thermal lens whose refractive index is falling off. So here's the the rho equals 0 line, and then the refractive index is maximum in the center, and then it falls off, right? So if the refractive index decreases with temperature, then what's happening to this wave? Well, you know that the refractive index is nothing but the speed of light in vacuum divided by the speed of light in the medium, which implies the speed of light in the medium is c over n, right? And this tells me that if the refractive index on either side of rho equals 0 is decreasing, then the velocity must be increasing, right? So if the refractive index, when it's maximum in the center, the refractive index maximum in the center means that the velocity there is minimum, okay? So yeah, that's right. So if the refractive index in the middle is maximum, that's where the velocity is minimum. So that means that the central ray, maybe the wavefront, let's say it's progressed to about this point here, let's say. Well, because the refractive index is less on either side, then that means that the velocity, in that same time, the wavefront here has progressed maybe up till there, right? And same on the bottom. And so if the refractive index is maximum in the center and decreasing outward, then the wavefront, you'll notice, is now the line has become something like this and this. And so the wavefront at the top part is moving inward. It's because, the direction of travel has to be then in this direction. And this wavefront is moving like this. And so you notice that there is a focusing going on, right? Because the central ray travels slower than the outer ones, okay, which implies the beam focuses. Okay. On the other hand, if so on the other hand, if the refractive index increases with temperature outward from center, and so that's where it does something like that, okay? Then the central ray travels faster than the outer ones, and that implies the beam diverges. Okay, so I can draw that here. So let's say that here's the medium, and in comes the incident plane wave there, right? And here's the center, rho equals 0, and then what you would have is that the center, because the refractive index is least in the center, so it only travels so much. So in this case, the refractive index, so did I get this right here? Yeah, and decrease of temperature. Yeah, that's good. Here, the refractive index is smallest in the middle, so actually this goes out a whole lot further. So I kind of live editing here. So this actually goes out further but then the sides don't travel out as much, right? And so you notice that the wavefront now looks like this and this. Yeah, and so it's now a diverging wavefront. Okay, so so that's why this is called thermal lensing. Now, of course, this still we haven't answered the question that how to avoid thermal lensing in a high power laser. That's the big question, and the answer is that we will exploit we'll exploit or rather, avoid thermal lensing by exploit birefringence. Okay, so make the gain medium, because the gain medium is the one that heats up the most, you see. So that's the one where you want to avoid the thermal lensing. So make the gain medium a highly birefringent material. Okay, now of course that's the answer, but how does it work? So that we're going to do in, I'm going to chop it up, so that will be the next video. Okay, so hold on to your horses. The answer is in the next video on how, by making the gain medium a highly birefringent material, we can avoid thermal lensing. And I do want to add to these notes here that we said the intracavity elements such as the gain medium are all relying on Brewster's angle, but really it's the gain medium that heats up the most. So I just want to add in here that gain medium is the intracavity element that heats up most, so we will try and avoid thermal lensing inside the gain medium. So that's why here, N element, intracavity element, and really it's the gain medium that we worry about the most. Okay, all right, that's my next video. All right, so see you on the other side. Just a sec.